In this session, I shall prove this trigonometric identity. Sine a plus b is equal to sine a cosine b plus cosine a sine b. This is one of the more complicated identity that is actually quite hard to memorize. And this is the first one. I shall prove that, and then after proving the first one, I shall go on to prove the remaining three, which would be easier making use of the first one. So the remaining three go something like that. The second one looks very similar to the first one, except that I have a minus sign here, a minus b, and I have a minus sign here also. So that's both signs change. The next one is cosine a plus b. So here it would be different. It would be, instead of sine a and cosine a, I have both cosine. I have cosine a and cosine b, and I have a minus sign here, and I have a sine a sine b. So this looks quite different from the last one. And then I have cosine a minus b equals to cosine a cosine b plus sine a sine b. So these are the four identities. Let me start with the first one. Alright. The way to do it is to first draw a triangle. Now, as always, we have right-angled triangle for trigonometry. Now I'm going to draw this triangle like that, with showing two angles, and I'll let this be A, let this angle be B. That would be my right angle, and this longer side I'll let it be 1. Right. Now looking again at what we want to prove, I want to prove something about sine of a plus b that is related to all these. And I'm going to try using this triangle to relate the sides of the triangle to each of these terms. I'll start with sine of a plus b, because a plus b is this overall angle here. So therefore the sine of a plus b, if I look at this triangle, is the opposite over the hypotenuse, and since this is 1, it means that this height itself is sine of a plus b. Now I'm just going to draw a line on one side to remind myself of this fact. Okay, so that's the height, sine of a plus b. Now I'm going to try to bring in all the sine and cosine of a and b. Right. Now this part is a little bit tricky. It's a bit hard to think of it if you have not seen this before. This is what we do. I'm going to draw a right-angled triangle over this, with this as the longest side, this as the acute angle. So this means that my right-angled triangle has to be formed by extending this line and drawing a perpendicular like that. So this gives me a new right-angled triangle with angle B. Right. So now I'm going to try and write down the expressions for some of the sides and see where that leads us. So first, if I have if I look at this new triangle, I can see that the side here is the opposite to B. So this side must be related to the hypotenuse and the angle by sine B. Right, that's just sine B. And if this is sine B, then I have a sine B there. If you look at the term there. Now apparently sine B is next to cosine A. So how might we be able to bring in this cosine A into the picture? Now A is there. If I just look at this right-angle triangle, that could be, this adjacent will be related to cosine A. Alright, but it's not obvious. It's not obviously connected to sine B. But if we look at this angle, notice that this angle is equal to that angle. So maybe that's how we can relate them. Okay, it's getting a bit bright. Let me adjust the brightness. Give me a second. Okay, that's better. Now notice that this angle, these two angles are the same, and those two angles are the same, of course, they are right angles. So therefore this angle must be the same as that angle. And that gives us our connection between A and sine B. If I look at this, and I think of sine B cosine A. What does it mean, sine B cosine A? If I look at this angle and this side, you see that cosine A, if I take sine B times cosine A, I can imagine that sine B is the hypotenuse but it can't be the hypotenuse of this right angle triangle because it's next to the right angle. So if I want to think of sine B as the hypotenuse, I have to make yet another right angle triangle. I drop a perpendicular from this corner to this side. So I can turn that side into the adjacent. Drop yet another right angle here. And if I do this, I'll find that this length here is in fact sine B times cosine A. I'm going to write it out here before it gets too crowded. Sine B cosine A. So now we actually have a physical meaning for this term. Now you can guess what the next step would be. We need to figure this out. Now we already have a physical meaning for that, which is this overall height here. And we have a physical meaning for that term, which is this height here. So surely that term there must be this remaining distance. So let's check that out. We must somehow be able to relate this distance to sine A and cosine B. Now, how can we do that? This distance. How about if I think about this line here? If I think about this line here, then this distance is the same as this distance. Let's try and find this distance. Now this is the opposite to the angle A, so it would be related to sine A. Okay, and this this side here, this side is the hypotenuse for this triangle, but it is also the adjacent to that right angle triangle. So this side is related to cosine B. In fact, this side is just 1 times cosine B. That is the length of this side. Okay, so all the way from there to there. That's cosine B, right from there all the way to there. And now we have the hypotenuse for this triangle, and since this is A, this must be the hypotenuse, cosine B, times sine A to give the adjacent. So finally we have a physical meaning for this term. And therefore, since this plus this, which is sine B cosine A, is equal to the overall height, which is sine A plus B, we can now write down this observation. Sine A plus B, which is the total height, is equal to this length, sine A cosine B, plus that length, which is cosine A sine B. And that completes the proof for the first identity. Moving on to the next identity, we see that the difference is a change in sign. I have a minus B here instead of the plus there. And one way to try is to simply replace all the b's in the first identity by minus b, and see if we can arrange it to give the result in number 2. I want to do the proof of 2. And in this case, let me start by saying that we would have to make use of this result, that sine of minus theta is equal to minus sine of theta, and cosine of minus theta is the same as cosine of theta. Okay, so I shan't prove it here, I shall just assume that this is correct. So now I want to replace b by minus b in this first identity. So this gives sine of a plus b, so from 1, which we have already proven. So sine of b changed to minus b, so sine of a minus b equal to sine of a times cosine of minus b plus cosine of a times sine of minus b. Now, making use of these relations, I have cosine of, if I cosine of minus angle, it gives back the cosine of the same angle. So the sign just disappears. So therefore cosine of minus b is the same as cosine b. I have cosine a here. Now sine of minus of angle become minus of sine of that angle. So sine minus b would become minus of sine b. Okay, and now therefore I have the result that I want. Sine a minus b is equal to sine a cosine b minus cosine a sine b. So this proves the second identity. Right, let me put in some light. Now moving on, to prove the third one, I need to somehow relate sine to cosine. Okay, so for the proof of the third identity, I need this relation, that sine of 90 degrees minus theta is equal to cosine theta. So again, I shan't prove that, I shall just make use of this. The way to make use of this let's see. I can try replacing A by right, okay, I'm going to try this. I'm going to try replacing B by 90 degrees minus B, perhaps. No, okay, I'm going to try this. I'm going to try replacing A plus B by 90 degrees minus the whole of A plus B. Right. So let's try that and see what happens. Remind yourself of the first identity. I'm going to make use of the first identity. So from 1, I'm going to write down sine of 90 degrees minus A plus B. Okay, let's see how I can make use of this. This would be, now to make use of this, I need to somehow rearrange this in a form where I have just angle plus angle. Rather than having 3 separate angles, I need to lump them together somehow so that I can make use of those. Let's see. So I'm going to write this as sine of, say, 90 degrees minus A minus B. Okay, I'm going to rearrange it this way. So now I'll think of this as one angle and this as another angle. So angle minus angle, which is with a sine of an angle minus angle, which is actually identity 2. Right, so I might actually use 2 instead of 1. Okay. Alright. Next, I'll say sine of 90 degrees minus angle is equal to cosine of the angle, as I mentioned just now. And then I make use of the second identity here, angle minus angle. So angle minus angle. So instead of A, I have 90 minus A. Alright, so I would replace the A there and the A there by 90 minus A. So let me copy this out now with that substitution. So I have sine of 90 degrees minus A for this times cosine B minus A replaced by 90 minus A. So cosine of 90 degrees minus A times the sine of B. So that's looking good now. Now, and if you remember the relation for sine of 90 minus A and cosine of 90 minus A, that is just cosine A, and that is just sine A. So making these changes, I can write down the result. Let's copy cosine B, copy sine B. And this is exactly the third identity. So this completes the proof. For the fourth identity, take a look, just this one. the difference between 4 and 3 is that b is changed to minus b. Now if I look at the third identity, b appears in cosine b and sine b. So it looks like we would have to make use of this identity, this relation again, for negative angles that we used in the proof for identity 2. So let's follow the same approach as in this earlier proof, where I replaced b by minus b. So I'm now going to replace b by minus b in the third identity. So I'm now doing the proof for the fourth and the last identity. I'm going to make use of 3. I'm going to replace b by minus b in that identity. That's the third one. So this gives cosine of a minus b. Alright, the b changed to minus b. And now cosine of a, cosine of minus b. Sine of a, sine of minus b. Right, and then we have cosine of minus b is, let's look back at the relations. Cosine of minus b is cosine of theta minus theta is cosine theta with no more signs. Sine of minus theta become minus sine of theta. So if we use it here, cosine of minus b is cosine b. Sine of minus b is minus of sine b. Finally, simplify this. Minus minus is a plus. We get the identity that we want to prove. And this completes the proof for the fourth identity. Now, using these 4 identities, we can prove 3 more that are quite commonly used. Let me adjust the light a bit again. Okay. So this is what I'm going to do now, right? I've done the first half of this session. In the second half, just a short half, I want to prove 3 identities. Now I'm changing the label now to no, maybe I shouldn't change. I'll just follow on. So I've proven 4 identities. This would be the number 5, 6, and 7 that I shall now prove. Right, number 5 is sine 2a equals to 2 sine a cosine a. Number 6 is cosine 2a is equal to cosine squared a minus sine squared a. And tangent 2a is equal to 2 tangent a over 1 minus tangent squared A. It will be these three. Starting with 5, right? The proof for 5. Sine 2a. The way to do this, going back to the earlier identities, is to make use of this. Okay. Now see, I want to prove something about sine 2a, and I know this formula for sine of a plus b. So what I can do is I can take the b as equal to a. Then I have a plus a here, which is just the 2a. Right, so that's one obvious way to try. So I'm going to write this out. I'm going to make use of using 1. I'll let b be equal to a. Now if I just substitute a into all the b's, let's see what happens. We have sine, on the left side, sine a plus a. Okay. On the right hand side, sine a, cosine a. Cosine a, sine a. And you can simplify. That is a plus a is 2a. Sine a, cosine a, sine a. So those two are the same. So therefore I have 2 sine a, cosine a, which is exactly what I want to prove. So this completes the proof for this fifth identity. Now looking at the next one, cosine 2a. And if you recall that we already have proven a corresponding identity for cosine a plus b, we can most likely use the same way that I did for sine 2a by replacing the b here by a. So let me try this. I'm now doing the proof for this sixth identity. So I need to make use of this one, number 3. So using identity 3, I'll let b be a. Then I'll substitute a into all the b's in this identity. So that would be cosine a plus a, cosine a, cosine a, sine a, sine a. And that's it. If I simplify, I have cosine a plus a is 2a, cosine a is cosine squared a, sine a is sine squared a. And if I now look at what I wanted to prove, this was what I wanted to prove, that cosine 2a is cosine squared a minus sine squared a. And here I have arrived at cosine 2a equals to cosine squared a minus sine squared a. Exactly the same. So this completes the proof for this number 6 identity. this last one is number 7, which is tangent of 2a equals to this. Now the way to prove this is to make use of the previous two results, because we now know that tangent is equal to sine over cosine. So why not try dividing number 5 by number 6, dividing those two, and see if it works. So here the proof for identity number 7. So I'm going to divide the two, divide 5 by 6. 5 by 6. Okay, so on the left hand side, I'll have sine 2a over cosine 2a. On the right hand side, I have 2 sine a cosine a over, that's a 2 there, over cosine squared a minus sine squared a. We'll try and simplify that. That left hand side would be tangent to a. And on the right hand side, now if we look at what we want to prove, right, this one, you see that on the right hand side it is all tangents. We don't have sines or cosines, but at this stage I only have sine and cosines here. So what I must do is I must relate this to tangent, and I know that sine over cosine gives tangent. So what I could do is I could divide the top and bottom by cosine. So 2 sine a cosine squared a minus sine squared a. I can divide the top by cosine a and the bottom by cosine a. Now I might hope that this cosine will cancel with this cosine, and that if I have sine over cosine, that turns into a tangent. So I need 2 factors of cosine, and likewise for the bottom. Now if I divide them out, the cosine cancel with 1 factor of cosine. Sine over cosine gives tangent. And at the bottom, I need to divide each term by cosine squared. The first term is cosine squared, divided by cosine squared gives 1. Second term, sine squared over cosine squared gives tangent squared. Right, so now I have the right hand side in just tangents, and if I compare this with what I wanted to prove, which is this one, you see that they are exactly the same. So this completes the proof. And finally, there are 2 remaining, this should be the last 2 identities that I want to prove, just to complete this whole set. There's quite a lot of identities. This would be number 8 and number 9. I think that's all I want to prove for today. Right, these are 2 alternate forms of the cosine 2a formula that I just proved. One is that cosine 2a is equal to 2 cosine squared a minus 1, and the other is 1 minus 2 sine squared a. So these are two forms that are also often used in mathematics. Okay, I'll start with the proof for 8. Now in this proof, I need to make use of two identities. I need to make use of cosine squared theta plus sine squared theta equals to 1, which we have seen just now, and I need to make use of also the previous, the first identity that we've seen, we've proven for cosine 2a. We want to start from here. So let me start from here. Use this identity 6. Cosine 2a is equal to cosine squared a minus sine squared a. And using this, I would now want to show that this is equal to this identity 8. Now again, we can take some ideas from this final result, that on the right hand side there is only cosine, there is no more sine, whereas in this starting identity I have a sine there. So what I could do is I can use this identity to write sine squared in terms of cosine. For example, if I rearrange this, I can get sine squared theta equals to 1 minus cosine squared theta. Alright. So therefore, sine squared theta is, sine squared a is 1 minus cosine squared a. If I remove the brackets, I get cosine squared a minus 1 plus cosine squared a. So finally, cosine squared a plus cosine squared a is 2 cosine squared a minus 1. You now compare this with this, you see that they are the same. So this completes the proof. Now for the part 9, it's very similar to this proof, but instead of expressing sine in terms of cosine, we go back to part 6 and we express cosine squared a in terms of sine, starting from the same formula. So this is the proof for identity number 9. Okay, so I would start from again 6. We have cosine 2a equals to cosine squared a minus sine squared a. I would then make use of the cosine squared theta plus sine squared theta equals to 1 identity. Express cosine squared in terms of sine squared. I can see that if I move this over to the other side, I get cosine squared theta is 1 minus sine squared theta. So this is what I need. So this is 1 minus sine squared a minus sine squared a. Okay, if I simplify this, I have 1 minus sine squared a minus sine squared a is minus 2 sine squared a. If I now look back at this, you see that we have 1 minus 2 sine squared a, which is exactly what I obtained down here. So this completes the proof. And that is all for this session.